Hello everyone. We are moving along in our introductory topics for the Calculus 1 course. In this section we will look at operations on rational expressions. For those who aren't familiar with them, a rational expression is the quotient of two polynomials. In other words, it's a fraction, and therefore it obeys the same operational rules as fractions do. In particular, the rational expression n1 over d1 and n2 over d2 can be added or subtracted only if their denominators are common. The same two rational expressions can be multiplied by multiplying their numerators respectively and their denominators. Finally, the division of the rational expressions can always be replaced by changing the divider n2 over d2 into a multiplication d2 over n2. In other words, we're replacing the dividing rational expression by its reciprocal. In many cases, these operations will be made easier if we use factoring. So all techniques you've seen in prior videos can be of great use here. Notably, we have simple factoring, grouping, we have the sum product method. Let's start with addition and subtraction. So we're going to use an example to show the steps that we will take in order to compute the addition or the subtraction of rational expressions. For example, let's compute the sum of 2x plus 1 over x squared plus 2x, which is added to the rational expression 3x minus 5 over x squared minus 4. As a first step, we will factor the denominator of each of these rational expressions. In the first case, simple factoring can be used to replace x squared plus 2x by x times x plus 2. In the case of the second rational expression, some of you will have recognized a difference of squares. X squared minus 4 has been replaced by x minus 2, x plus 2. At this stage, we can take note of values of x that are acceptable or not. Keep in mind that rational expressions are defined as long as their denominators are not 0. The first rational expression is undefined if x is 0 and if x is minus 2. A third value adds on to the two others when we take a look at the second rational expression and recognize that x equals 2 would also create a 0 denominator. Now we're going to identify the lowest common multiple of the denominators and rewrite each fraction with this expression as the denominator. Notice how the first and second rational expressions in their factored forms have an x plus 2 at their denominators. However, the first rational expression does not have the x minus 2 factor that the second one has. Likewise, the second rational expression does not have at its denominator the x that the first one does. Basically, we're filling in the factors that one rational expression is missing relative to the other. We're multiplying above and below to guarantee that the individual fractions have not changed values. Now we can regroup the fractions by adding their numerators together. These are properties of fractions that we've seen previously. Expand the numerator and collect the terms and determine if additional simplifications are possible. So on the numerator, now we'll proceed by expanding and regrouping like terms. In this particular example, if 5x squared minus 8x minus 2 could have been factored some more, we would have actually gone through that process. Okay, so in conclusion, the addition of the rational expressions 2x plus 1 over x squared plus 2x with 3x minus 5 over x squared minus 4 can be replaced by the rational expression that you see on the right. Again, in terms of where this rational expression is defined, depends on values of x that do not create zero denominators. So this equality is true for all x, that is, neither 0 or minus 2 or plus 2. Then comes multiplication. Once again, we're going to use an example to show what steps can be taken in order to multiply rational expressions. Here we're going to compute the product of the rational functions, or the rational expressions, 4x plus 4 over x squared plus 2x, and 3x squared plus 6x over x squared minus x minus 2. This time we're going to factor both the numerator and denominator of the individual rational expressions. Okay, so techniques seen in prior videos are super useful here. In the first rational expression, both numerator and denominator can be factored by simple factoring, 4 being a common factor to the numerator and x to the denominator. As for the second rational expression, the numerator has a 3x expression, or 3x term that can be factored. As for x squared minus x minus 2, I've used the sum product method in order to factor it into x minus 2, x plus 1. Once again, you can take note of values of x that are allowed when computing this product, especially in a factored form. They are much easier to identify. X equals 0 minus 2 would create 0 denominators in the first rational expression. X equals 2 and minus 1 are prohibited from being used in the second rational expression. So 4 values of x are prohibited in this computation. Now we're going to identify all the factors that are present at both numerator or denominator, or present at both the numerator and the denominator, from either rational function. I've highlighted these factors with colors, so you've noticed x plus 1 appeared at the numerator of the first rational expression and at the denominator of the one it was multiplying with. Same goes with the factor x. That was a denominator in the first rational expression and a numerator of the second. And same goes for x plus 2, which appeared at one's denominator and the other's numerator. Having these common terms at the top and bottom now allows you to eliminate them. And, in the end, remaining terms at the numerator are 4 and 3 that multiply to give 12. And at the bottom, all that's left is the x minus 2. Very important to note that when we did these cancellations, the fact that x could not be 0, could not be minus 1, and could not be minus 2 are worth noting. Because remember that in the previous step, we had 0 dividers for these 3 values. As for x equals 2, it's still a prohibited value because 12 over x minus 2 is undefined, but at the very least it is still there for us to detect. Okay, so in short, we have reduced the product of the original rational expressions by replacing it into a simplified form, 12 over x minus 2. Now this identity is true for the considering the list of exclusions that we noted along the way. Finally, we're going to look at division, and again use an example to describe the steps for which a quotient of 2 rational expressions can be computed. So this time we will calculate the quotient of the rational expression x squared minus 1 over x squared minus 2x, which is dividing 3x squared minus 3x over x squared minus x minus 2. Once again, we will factor the numerator and the denominator of each individual rational expression. Okay, and from the first rational expression, we had a difference of squares occurring at the numerator and simple factoring where x was common at the denominator. In the dividing term, 3x squared minus 3x was factored, and the sum product method was used to break up the denominator. The rational functions exist individually as long as x is not 0 and x is not 2. Those are the restrictions we have to impose to the first rational expression. And another one adds on when we consider the dividing rational expression, which is also undefined at -1. So based on rules for the division of fractions that we've seen previously, we will convert the division of the rational expression by a multiplication where n2 over d2, so the dividing rational expression is replaced by its reciprocal. Right, so here we had the factored forms, and now we will replace the division by a multiplication. And you've noticed the dividing rational expression has been converted into its reciprocal expression. Then we can start looking for factors that are present at both numerator and denominator, and we'll figure out if any simplifications can take place. Again, if you have color, then this is super useful to observe what is replicated top and bottom. So this time we've noticed x minus 1 is a factor that appears at the numerator of the first fraction and at the denominator of the second, and vice versa where x minus 2 is concerned, so dividing in the first rational term and a numerator or part of the numerator in the second. And therefore now we can proceed with cancellations and get the reduced form where x plus 1 was multiplied with itself at the numerator and x was multiplying with 3x squared. Some prohibited values have disappeared in this cancellation, so perhaps we should take note of them. So x equals 1 and x equals 2 created zero denominators originally, and they've disappeared. That doesn't give you the right to use those values all of a sudden. Okay, so in conclusion, we have simplified this quotient into x plus 1 squared over 3x squared. But a lot of restrictions are imposed in terms of where this equality is true. In the case of x equals 0, it's still there for us to see. We can clearly observe in the reduced expression that x is not allowed. All three other values, minus 1, 1, and 2, are caused by operations we've done or by values that created undefined moments of the original rational functions.